Okay, so we're going to look at some word problems that result in exponential equations. So in this first one, 11 o'clock, Sally sits some yogurt out, and it has one bacteria in it. Every minute that goes by, okay, so 11 a.m. for Sally, one bacteria. Every minute that goes by, it increases, the bacteria in her yogurt increases by a factor of 4. So remember, a factor of 4 means it multiplies by 4. All right, 25 minutes later, so at 11:25, another kid, Lupe, leaves her yogurt on the heater. Being on the heater, the bacteria is going to increase at a much greater rate. So the number of bacteria in Lupe's yogurt, again, it starts at 1, but hers increases by a factor of 8 every minute. So our question is, at what time will the number of bacteria in each yogurt be the same? Now, same in math implies equal. Okay, so that's why we're going to write an equation here to answer this. Now, like any word problem, we need to start with our let statement. And x is going to represent how long it takes, okay, because we want to know at what time. It's important that you always have your let statement, your variable, stand for the time that has passed, in this case minutes, since the whole problem began. Now, since that means 11 a.m., because that's when Sally put her yogurt out. So we want to let x equal the minutes past or since 11 a.m. Okay, not since 11:25. Right, now, the equation here, okay, with two sides, we want the two amounts of yogurt to be the same, to be equal. So one side is going to represent how much bacteria is in Sally's yogurt. The other one will represent how much bacteria is in Lupe's yogurt. Well, let's see. In Sally's yogurt, she starts with one bacteria, and it multiplies by 4 every minute. So multiplies by 4 is our indicator that this is exponential. Multiplies by 4, how many times? Well, I don't know, but every minute, so x minutes. Lupe, her bacteria also starts with 1, but it's increasing at a greater rate, multiplying by 8. So her base is 8. Her exponent, though, is not x, because x is how many minutes past 11 a.m. Well, she didn't put her yogurt out at 11 a.m. She waited 25 minutes. So however long Sally's yogurt has been out, Lupe's has been out 25 minutes less than that. So x minus 25. In order to solve this exponential equation, we first need to turn this 4 and this 8 into common bases. Now, it's tempting to try to say that 8 is 4 squared. It is not. 4 squared is 16. So I'm going to have to change both bases. So what power can I write both 4 and 8 as that has a common base? And the answer to that is 2. So 4 is 2 squared. And then I still have this x outside. We want to know when that equals 8 is 2 to the third. And I have x minus 25. Using the power to a power rule, I multiply 2 times x. This is 2 to the 2x. Multiply here, and it's the exponent 3 times the entire x minus 25. So I need to distribute. That becomes 2 to the 3x minus 75. Now, once I have the bases the same, what we learned was that means the exponents must also be equal. So therefore, I can write myself a new equation that sets the exponent for Sally equal to the exponent for Lupe, 3x minus 75. Solving this, there's x's on both sides. Subtract 3x. So 2x minus 3x is negative 1x. That's equal to, don't lose this negative sign, negative 75. Divide both sides by negative 1. X is equal to positive 75. Now, what does that tell us? Positive 75. Well, if we go back to our let statement, that means it has been 75 minutes past 11 o'clock. Well, what time is that? The question actually says at what time. So 75 minutes past 11. Well, 60 minutes past 11 would be noon. Another 15 minutes makes it 12:15 p.m. Okay, number 2. At noon, a computer virus infects 1 kilobyte of a computer's memory. Every minute thereafter, the number infected triples. Okay, so there's again why we know that it's an exponential equation. It's being multiplied by 3 every minute. Okay? At 12 minutes after noon, so this is the second one, a much worse computer virus infects 1 kilobyte of another computer's memory. Each minute thereafter, this amount is multiplied by 9. When will the number of kilobytes infected be the same? Okay, so we know we want equal in both computers. So our let statement again, we want it to represent the amount of time since the first computer was infected. Well, that happened at noon. So X is going to be the minutes past or after noon. All right, well, this first computer started with 1 kilobyte, so we just have to triple that 1 kilobyte every minute. When will that be equal to the other computer is multiplying by 9 every minute, but it was only being multiplied 12 minutes less than the first computer. So X minus 12. Okay. Going through the same steps as the last problem, we need common bases. Well, 3 and 9 can both be written as powers of 3. So we leave 3 to the x as is. We change 9 into 3 squared, and I still have exponent x minus 12. Okay. Power to a power says I need to multiply the 2 times the x minus 12. So 3 to the x is equal to 3 to the 2x minus 24. Once the bases match, I can set one exponent equal to the other exponent and solve that equation. So x equals 2x minus 24. Solving this, subtract 2x on both sides. So negative 1x equals negative 24. Divide both sides by negative 1. X is equal to positive 24. Now this was kind of vague when it said when will the number of kilobytes infected be the same. So it's 24 minutes after the first computer was infected, or since we knew that was at noon, we could say this happened at 12:24 p.m. All right, number 3. Beginning of the year 2000, geologists discovered a rock whose weight was estimated to be 1 megaton. Okay, so this starts in the year 2000 with 1 megaton. Each year, the mass of the rock, now this is our first time saying decreased, but it's by a factor of 2. So the phrase factor of 2 tells me multiplies, but since it's decreasing, it's multiplying by 1/2. Almost like it's dividing by 2, but we have to consider everything as a multiplication problem. So we're multiplying by 1/2. Now, at the beginning of 2010, the second rock was also 1 megaton, and each year that one decreased by a factor of 4. So this one multiplies by 1/4. So after how many years will they be the same or equal? So let x stand for the amount of time, in this case it's years, since our problem began, which was the year 2000. Years after 2000. Okay. So this first rock with the 1 megaton beginning multiplies by 1/2 every year. So we need to enclose that 1/2 in parentheses to say the entire fraction is raised to the exponent of x. When will that be equal to, now the other rock is multiplying by 1/4, but not for as long. This started 10 years later than the other rock, than the first rock, so this has only been happening for x minus 10 years. So again, first step, get common bases. Now, these are fractions, but we know that that just means using negative exponents. So I'm really just looking at the 2 and the 4 and saying, what can be a common base for 2 and 4? The answer to that is 2. So 1/2 is really 2 to the negative first. I still have the power of x on that. That needs to be equal to, now 4 is really 2 squared, so 1/4 is really 2 to the negative 2. And then outside the parentheses, the exponent is x minus 10. Use the power to a power property to multiply. This is 2 to the negative 1x. Here to multiply, I need to distribute, so it's 2 to the negative 2x plus 10. Negative 2 times negative 10 becomes positive 20. Okay, now that the bases match, I can set the exponents equal. So negative 1x will be equal to negative 2x plus 20. To solve that, I'll add 2x to both sides. So negative 1x plus 2x is x equals 20. So after how many years will the masses of both rocks be the same? The answer is 20 years. And last one. Number 4, at the start, one person wears red socks to school. Every day, the number of people wearing red socks doubles. So once again, this is why we know it's exponential, because doubling means multiply by 2. On the 8th day, so 8 days later, one person wears an ankle bracelet. Each day after, the number of people wearing ankle bracelets increases by a factor of 4. So that means multiplies by 4. On what day will the number of people wearing red socks and the number of people wearing ankle bracelets be the same, or in other words, be equal? So start with our let statement. X will be, in this case, we're talking days, so the number of days after the first trend started. So the first trend was a red sox, so days after red socks began. Okay, so one person wearing red socks, and that doubles. So that's 2 to the x. I want to know when that will equal the number of people wearing ankle bracelets. Well, that started with 1 multiplied by 4, but that did not go on for as long as the red socks. So this was started 8 days later. So my exponent is x minus 8. All right, we need common bases. What powers can I write for 2 and 4 with the same base? Again, they can both be written as base 2. So I'll leave 2 to the x as is. 4 I'll change to 2 squared, and I will not lose the x minus 8 exponent. Using power to a power, I need to multiply here. So 2 to the x is equal to 2 to the 2x minus 16. Now that my bases match, I can set the exponents equal. X equals 2x minus 16. To solve that, subtract 2x from both sides. 1x minus 2x is negative 1x, equals, can't lose this side, negative 16. Divide both sides by negative 1. X is equal to positive 16. So what was my question again? It was, on what day will the number of red socks and ankle bracelets be equal? It's on day 16.